so I've hit record. Okay, yeah. So in order of importance, in my opinion, I can speak for civil engineering. It's like the topics from this term. Bending is the most important, and then probably axial forces, and then deflections, and then buckling. Okay, in that order. So I don't know why they don't assess buckling, to be honest with you, because it's definitely one of the most important things you need to know for civil engineering in general, and for structural and for mech. They do it a lot. So if you're designing like an airplane or whatever you do in mech, super important. So I do want to actually spend some time explaining to you guys, because it won't directly impact you right now, but not learning it now will. I think it'd be better to learn it now so you get a good foundation for the future, right? Like in steel structures, for example, next year. With that said, I do, want to be kind of quick with this workshop so that you can ask me questions about the stuff that you might have questions about for the other topics which will be assessed. Okay, so yeah, we're basically at the end of the list of stuff for this course, and you should be pretty familiar with everything. So as I mentioned, the topics which will probably be in your finals: bending, deflection, shear and torsion is 50-50, I reckon, in terms of what's actually assessed. Okay, so what's this topic actually about? So it's kind of relates solid mechanics to the material science stuff, right? So you've learned about what stress and strain and stuff are. And then this topic's like putting into perspective some theories that people have on the behavior of materials. So broadly speaking, there's two groups. There's ductile materials and there's brittle materials, right? So ductile materials, you can think of it like steel, aluminium, these kind of things. Since they're like in a metal lattice, right? If you remember chemistry on that side, they behave in a ductile manner. They won't break suddenly, essentially, right? So there'll be a bit of yielding before it completely fails, right? And then brittle materials, so I might just draw that on a stress strain curve just to illustrate my point. So if you have a material curve, stress strain, you've got, for a ductile material, it might look something like this, right? Where you've got an elastic region, a plastic region, which we can just pretend is completely flat. And then it might actually also have a bit of strain hardening before it completely breaks. So that would be like a definition of a ductile material. For a brittle material, okay, it might look something more like that, or a very, very small plastic region before it snaps. So examples of brittle materials would be like concrete, timber in tension, what else? Glass, I guess. Yeah, like usually ceramics and even composite materials like carbon fiber are brittle, okay? And so we have these different theories to describe them. Oh, and another one is, if you're doing soil mechanics in Term 3 as a civil engineer, Moore's failure criterion. It's kind of funny because I cover it in like the lecture slides for this course, but there's actually no questions to to practice off of for Moore's failure criterion. But that's the last topic in soil mechanics as well. So soil would be like a brittle material essentially as well, right? And another brittle material would be like rock, for example. Okay, so that's just some examples of how that overlaps. So I want you to quickly remember this formula. So this is from the week 2 topic, stress, and it's where you're finding the principal axes. So let's say you've got a Moore circle that looks like that. Okay, finding stress 1, stress 2. Okay, so this is stress, and then this is strain. No, that's not right. It's that one. Yeah, and you've got just 2 random points. Let's call them that and that. Okay. You're trying to find these points here. So maximum and minimum principal stresses, right? Okay. The first one's called max shear stress theory, and essentially, okay. So there's basically 2 scenarios. Okay. Let me just show you. Let me skip forward for a second, right? What we're gonna do is we're gonna put this on a graph, but it's not gonna be the one that you've seen before, right? instead of being like this, where you're mapping like the shear stress and the axial stress, you're going to instead be mapping the principal stresses, okay? Like that. Okay. And then you're going to see something called a failure envelope, right? So what it means is everything contained within this region, so what I've highlighted in yellow or green, is going to not fail. And anything outside of it is going to fail. So remember, this is for ductile materials, so it will basically yield outside this point. Okay. Oh, sorry, outside this envelope, it's called. So what all these formulas, which I'm about to show you on the previous page, are describing, are basically describing the line equations here that you see. Okay, so these ones. So they're going to be in terms of absolute value, because so in that line I just drew in blue, that'll be one of the equations. This will be another equation. This will be another equation, okay? And you're just trying to find if a point that you're interested in falls outside of what I just drew. Okay, so this makes more sense when I show you the thing. So, okay, if you remember, let's just say unit circle, right? No, it's garbage tray. Yeah, so unit circle, if you remember, if you have an x and a y that's positive and they're multiplied together, it's positive over there, and then it's positive here, and it's negative here, and it's negative here, right? So the idea is that if your principal stresses are of the same sign, they fall into one of these quadrants, right? And if they're a different sign, which I'll show you below, they'll fall into different, like the second and the fourth quadrant or whatever, right? So the idea is we're looking at the purple ones, right? So the positive quadrants first, and the equation to describe that is this. Okay, so the max axial stress before it yields is the maximum between these two. Okay, absolute value. So absolute value, you'll see later, but it basically makes it so that. Okay, I'll show you later. Okay, so basically on a Moore's circle, if your principal axes are both like to the right or to the left, like they're the same sign, okay, then you use this formula basically, right? And then you use this check to check if it's yielded. But if they're of opposite signs, so one's to the left and one's to the right of your y-intercept, I guess, you use this formula instead, these formulas. Okay, so that's basically the theory. It's like super abstract, to be honest, but when you see the numbers punched in, it just clicks. It makes a lot more sense. Here's me graphing this on Desmos to show you what I mean. The idea is, so if the x direction is sigma 1 and the y direction is sigma 2, the green lines, that's how it's reflected. The green lines are the absolute value things, so it goes on either side of it. And the purple lines are like there and there, so it's reflected from the x-axis, x-intercept. And then the blue line's that one. It's doing blue. Okay. This one's the other one that I'm going to talk about later. But you're basically equaling. You're checking. Sorry, it being equal is basically talking about that's the limit. So that's the yield stress. Okay. So when you set this equation equal to the yield stress, that's that line. And anything greater than that falls outside of the envelope, the failure envelope, and therefore will yield. Okay. So that's kind of how this works. All right. All right. So let's see this in a question. You've got a steel shell, which implies that we're working with a ductile material, right? And we want to determine if the failure due to yielding has occurred on the basis of maximum shear stress theory, which is what we're doing. And then just take the max shear stress as 250 MPa. Okay. You're given all this information. Oh, sorry. You're just given this little diagram. Okay. So it's a stress element, a plane stress element, and we can figure out, we can back work all these values by looking at it, right? So if you remember from week 2, looking at this, so tension being positive sign in the x direction gives you 70. Compression being negative in the y direction gives you negative. And the shear pointing in the top right corner gives you a positive shear value, right? Okay, so the first thing we're going to do is plug in our numbers into the principal axis formula, right? This week, by the way, is incredibly straightforward. Or this topic, I guess. So we're literally just plugging in all these things into this formula, which gives us 5 plus or minus square root 5,825. Okay, that gives us 81.32 MPa and negative 71.32 MPa. Okay. So at this point, you're looking at these principal stresses that you figured out, and you're like, okay, they're opposite signs, right? So in terms of our quadrants, we're working, x direction is sigma 1, I think. Sorry, give me 1 sec. Yes. And y direction sigma 2. So sigma 2 is negative, which means it goes below the curve, and then sigma below the x-intercept, and the sigma 1 is positive, so it'll be somewhere over here, okay? It'll be here or outside the envelope. So that's what we're going to check. Wait. Sorry. This won't be a circle. This will be like that or something, right? Okay. So we're going to use the formula which corresponds with the second and fourth quadrants, right? Which looks like this. And we're literally just plugging in those numbers, 81.32. You're doing a minus, but you want to make sure you still plug in a negative number, okay? So this will be added together, giving us 152.64 MPa. And since this number is less than the yield, okay, that's how you know our material hasn't failed, right? So in reality, we're sitting somewhere like here, okay? Oh, there we go, I've already drawn it. So the yield envelope is 250, okay, so that's over here. And then we're plotting on the x direction 81, and then on the y direction negative 71, okay? Okay. Therefore, we're not yielded, because it sits within our failure envelope. So since it's not outside of it, it hasn't yielded, okay? Does that make sense? All right. Because, again, this shit's not accessed, so I'm going to go quicker, but that's like the basic premise, right? Like, of what you have to do. I'll just show you some other theories, basically. So this one is called max distortion energy theory. It's similar because it's also a different theory for ductile materials, right? But instead of this kind of like diamond-shaped thing, right, described by 3 equations, we have this oval, right? And if I was to overlap them together, it would actually look like that. Okay, so this oval basically is a little bit bigger than the diamond that we had from the max shear stress theory, okay? And this oval can actually be plotted using a single equation, okay? So, yeah, it looks like this, right? And your yield strength is going to be plugged in on the right-hand side, and you square it. And when you do this on Desmos, actually, it perfectly aligns with these 4 points, okay? So I've just given an example of 10, just so it's easy to understand. But obviously, most materials aren't going to have a yield strength of 10. The materials you'll be dealing with would be in like the hundreds, basically, right? Hundreds of MPa. Okay. Okay. Any questions so far? No. All right. So that's the general idea. We've also got. So basically, what this one is now we're going to use. So this is another example. We're going to basically figure out. So this is a steel shell, so it's ductile. We have 700 MPa. We want to see if this has failed based on the first theory that we looked at and then the second theory that we looked at. Right. So we look at our stress element. We can deduce these parameters, and then we just plug everything in. Okay. So one sec. Oh, sorry. One sec. plug everything in. So this is 500. This would be -200. This is also 500. This is -200. This is 150. Okay, so you get 150 plus or minus 380.79. Okay, so that just gives us this and this. So these are, okay, well first I'm just going to talk about max distortion theory, max distortion energy theory. You literally plug in these numbers as you see them. Okay, so now this time you don't have to think about which quadrant they're in when you're using this formula. Okay, so these two will use this one, these two will use this number, and your yield strength, which was given as 700 MPa, will be on the right-hand side. You basically see, once you compute the left-hand side and the right-hand side, that the left-hand side is less than the right-hand side. And in terms of where it sits on our failure envelope, it's contained within that oval. Okay, so therefore it won't yield. Okay, does that make sense? Yeah. Okay, so part B is basically use that first theory that we saw before and just plug in the exact same numbers. So plugging that in, plugging in sigma 1 and sigma 2. And the yield stress, right? You see that because this time it's greater than the right-hand side, we've actually got a value which sits outside the failure envelope and it fails. Okay, so this is like an interesting case where when it's contained inside the oval, it doesn't fail, but when you're using the first theory, which is more conservative, it does fail. Okay, so that's what this question's trying to illustrate. So does that make sense? Yeah. Okay. So moving on to brittle failure theories. So there's two that they talk about. One's a max normal stress theory, which we'll see a question for. It's very similar, but we don't have these diagonal bits, right, to the first theory. And then we have Moore's failure criterion. So this one is how they test the properties of soil, right, in soil mechanics. So you do 3 tests. It's called a triaxial test. You test the soil in axial tension and see where it fails. You test the soil in axial compression until it fails, and then you test it in pure torsion, right? So you'll see what that looks like in a second. So you basically have like a cylindrical specimen of soil, and then you apply like a twist to it like that, and like that, and then you get some value, right? So the first test will give you this value out here on your Morse circle. The second test will give you this value out here on your Morse circle. The third test will give you this value on your Morse circle, okay? And from that you can deduce this failure envelope, which is what it looks like on a stress, shear and like axial stress graph, right? In terms of what it looks like on a principal stresses graph, it actually looks like that, okay? Yeah, anyway, so we actually don't talk about this in the course, but you will see it in soil mechanics, okay, if you're doing soil mechanics. Cool. Okay, so an example of that first theory, which I briefly mentioned about this one, the max normal stress theory, looks like this, okay? So here we've got a block of concrete, like a cylinder of concrete, right? And it's got compression forces acting on it, so you've got 2 kilonewtons of compression, and then you've got 500 Newton meters of torsion on it, okay? So if I was to graph, let me make this a bit smaller. If I was to graph, right, the axial stress, right, compression, it would look like that. So the whole thing's in positive compression, right? And if I was to graph the torsion moment diagram, it would also be like that, okay? Depending on your perspective, it's positive or negative torsion, but it doesn't really matter, okay? We just need the magnitude of torsion, okay? So the entire block of concrete is undergoing some amount of torsion and some amount of compression, okay? So yeah, it tells you the diameter, it tells you all those forces like I mentioned, and it tells you the limit. So the ultimate stress of concrete, they just say is 28 MPa, okay? So here you can start to see the parallels behind like what we learned, I guess, last week in terms of torsional shear, okay, and axial stress, okay. So we know that axial forces are a function of the area, right? So like this, since it's a circular area, right, we use the area of a circle formula. We have a diameter of 50, so just chuck that in, giving us 1,963.5 millimeters squared. And then we're converting 2 kilonewtons to 2,000 newtons, right? And then the axial stress that we're experiencing is 1.019 MPa, okay? In terms of shear, here we want the radius, okay, for the polar moment of inertia, polar moment of inertia, which would be half the diameter, and that gives us this value, okay? In terms of the torsion that it's experiencing, right, we want to convert this to Newton millimeters. So that gives us 500, and then we want to convert the meters to millimeters, right? So we times it by 1,000. And in terms of the shear stress formula due to torsion, that was from last week. We plug in 25 again. We plug in this value for torsion, and we plug in this value for polar moment of inertia, giving us 20.372 MPa, okay? So if I was to graph this on a Moore circle, it might look like this, okay? So this is axial stress and shear stress, right? And basically we're here and here, okay? So we found out that sigma y is 1.019, and we're gonna, okay, let's just take that as yx. Again, it doesn't really matter, it matters more the magnitude. That'll be 20.372, okay? And down here, so that's sigma yx, okay? Down here is sigma x, so that's 0, because we're not putting it into horizontal compression, or, oh, sorry, I should have drawn this the other way because it's in compression, isn't it? Anyway. And this one is the opposite sign of whatever you got for this one, okay? So I didn't draw that very well, but you get the idea, right? So you plug in everything to find your principal stresses, like before. And you figure out these are the principal stresses, and individually, if they're both less than the ultimate stress, then you're fine. So that's why it's a box, right? So in like the principal one and principal 2 both fall within the envelope of the ultimate stress that it can take, right? Okay. Any questions? All right, I'm going to quickly run through buckling, and then I'll see how far we get. There'll be a break, and you can ask questions about the stuff. Like we'll do a bit of a help session for the other exam stuff, right? Okay. Let's talk about buckling first, right? So buckling, as I briefly stated at the start, is super, super important for whatever type of engineering you're doing, and I don't understand, to be honest, why they don't assess it, because I think it's like a pretty critical learning outcome, right? Because you will use it in future courses, 100%. Okay, so basically the idea of buckling, right? So I've actually got some balsa wood for a demonstration, right? So, okay, I've got 2 pieces of wood. I've got one that's like rectangular cross section with pretty extreme differences between like the dimensions, right? And then I've got one which is like a square, okay? So just on the one that's a square, if I compress it, I'll do it so that the video can see it, it will just buckle, okay? So you can kind of see that the idea of buckling is if I load it and I unload it, right, it's going to return back to its original state. So the idea is buckling is elastic, right? Like an elastic band. If I stretch an elastic band and I let go, it'll just return to its original state. That's the idea. Buckling is an elastic failure mode, but if you imagine if I keep pressing this together in compression, there'll be a certain point which it breaks, okay? So that's called the critical buckling stress, okay? Which I can apply to break this, okay? Okay, so for a square, all right, I've got a question. So for a square like this, right, so square cross-section, we know the moment of inertia in the x and the y direction are the same, okay? So if you imagine a Moore circle, right, in your head, what does it look like for a complete like square shape? Right, so again, we're graphing a Moore circle, but this one will be your area moment of inertia, and this one will be your product moment of inertia. Okay, it'll look something like this. Okay, so the value you see here is both Ix and Iy. Okay, and in fact, if we were to go diagonal, right, it would also be the same number. Okay. So the idea is that if I'm pressing this in compression, it actually doesn't have a preferred buckling axis, right? Because it's a complete square. Okay. All right. Oops. What did I do? Okay. So Euler's buckling formula is basically this. So Euler's buckling formula tells you the critical amount of axial stress which I'm applying, right? So sometimes this is called N, right? Maybe N critical, but here it's called P, right? Such that it will break or whatever. Okay, so it's a function of all these different things. Pi is literally like, you type in your calculator that pi. E is the elastic modulus. I is this one, the area moment of inertia. And importantly, it's the minimum. Okay, so if this shape was like this instead, XX and then YY. Okay. YY bending is more critical. So if I go basically IY is less than IX, you'll be taking the critical one basically, right? So I show you like this, like a ruler shape basically. If I press, you know exactly which way it's going. It's going that way. Okay. It'll never go that way, right? Okay. But it's a ratio of that and LE. LE is also directional. I'll tell you a bit about that later. But KE is an end restraint condition, basically, right? So basically, if this is pins, right? So if I've got this balsa wood board and I'm not restricting the rotation at all when I press it together with my hands, right? It's going to form this perfect C shape in buckling, right? But if I grip it a bit with my hands, right? Do you see how the C shape is like restricted, right? So that's the second one that I've drawn there. So it's fixed. We say that the approximate amount is 50%. So you're thinking of what is the size of the C shape in buckling, okay? It ends up being about 50%, okay? So the other thing is if I hold one end with my hand clamped, like a fixed support, and the other one's free, it'll be about 70%, like that, okay? So this is called the effective length factor because we multiply this by the length, okay? So it's the length of the C shape, essentially, is what you're doing. And another case is if you have a cantilever that experiences like, basically it's like this, right? So if one hand is fixed at the bottom and then this one I'm pressing down, do you see how it like comes out a lot? So this one's not a support, it'll just be a point load or something like that. It will come out a lot bigger. And the idea is that the C shape actually ends up being about 200%, right? So twice the length. Okay, so it can extend past, like the imaginary line which makes a C shape can actually extend past the length itself, okay? So these, you'll learn about this more in like steels and etc. Okay, and even concrete. So the idea is we're comparing something called the slenderness ratio. So the slenderness ratio is your buckling length, right, over something called the radius of gyration. The radius of gyration, like, just think of it as a function of your moment of inertia, okay? Because radius of gyration is actually really hard to conceptualize. Like, I've tried to explain it, like, physically in many different classes, and I can't find a good explanation for it, okay? But I think mathematically it's actually quite simple to understand. Just understand it's the square root of the moment of inertia normalized by your area, right? So divided by your area. So it's some number that's related to your moment of inertia, okay? Okay, so sometimes you get questions like this, where it's restrained in one direction but not the other. So for an I-beam, right, we know that the moment of inertia going like bending about this axis, right, is going to be bigger than if it was bending sideways, right? But what happens if the sideways direction is restrained in the middle, okay? Like what you can see in this question. In which case, restraining it basically, instead of letting it buckle like a C shape, it halves the buckling length, and therefore it has to buckle like an S shape instead, okay? So a lot of the time in buckling design, you're comparing the moment of inertia or your radius of gyration by how long its unrestrained length is, okay? That's the idea. So for example, LEY in this question is 6 meters, but LEX is 12 meters, okay? So it's stronger in that direction, which it's going 12 meters unrestrained, but in the weaker direction, it's half that length. So you have to check which one will govern, right? So essentially the critical slenderness ratio is your maximum slenderness ratio, okay? So it's just the biggest between those two things. And then you basically, once you find out the critical direction, you can plug in these values, right? So if we find that this one's critical, you plug in this value and this value into here and here. But if you find that this one's critical, you plug in this value and this value into here and here, okay? That's the idea. So, yeah, that's basically it. Okay, I'll just run through these questions really quickly because, quite frankly, you've got better things to think about right now. But I still want to show you how these numbers kind of work. Okay, so this question says the bottom is fixed like that, and the top is pinned, right? So we've got pin at the top, we've got fixed at the bottom. If one side's fixed and one side's pinned, in this course we take this as 0.7, okay? And we know that 3 meters is 3,000 mil, okay? Next thing we do is we figure out the geometric properties, okay? So we basically just plug in everything. So this is a rectangular cross section. Okay, and then moment of inertia looks like this, and like that. Okay, so we know that because there's no restraints in the middle, right, for the weak direction is always going to govern, okay? So the idea is there's nothing restraining this, right? So we'll always bend about the y axis, similar to this balsa wood like piece, right? It's always going to bend sideways, like how you see it here, right? So therefore, we're going to use the lower moment of inertia because it's going to be the one that fails first, right? Your elastic modulus will be the consistent throughout. So it was 12 GPa, which is 12,000 MPa. Yep. And then the K factor is this one. So it depends on the restraints, the ends, and then your length is 3,000, okay? So once you do all that, you find that the critical buckling stress is 27.98 times 10 to the 3 newtons, okay? So once you do that, you want to find the critical buckling stress, right? So sorry, that was the critical buckling force. Now we just convert it to a stress by dividing by the area. So you get that number, you divide it by 100 times 50. You get 5.6 MPa. Let me fix up what I meant to say, okay? Sorry. Basically, this is the stress that causes buckling, right? So if I draw that column, right? If I apply 5.6 MPa of stress at the top, it's going to cause a column to buckle, okay? I need to apply I need to apply 35 MPa for it to yield, okay? So which one's going to happen first? Okay, sorry, that's what I meant to say. The buckling will happen first, right? So what happens, right, if I was to model... timber's a bit of a weird material curve. That's the wrong way. Timber's a bit of a weird material curve. In compression, it kind of looks like that. So it has a bit of ductility, but not really, right? Okay. So the idea is the yield stress might look like there. Okay. We're saying, right, if that's 35 MPa, all the way down here at 5.6 MPa is going to cause buckling in the elastic region, right? So buckling is like an early type of failure mechanism that can happen in the elastic region before your yielding happens, right? And it's all to do with how long your column is and its like cross-sectional properties, its stiffness, etc. Okay. So you have to check, like as a structural engineer, not only do you have to check how much stress before something yields, for example, you have to also check that against the buckling stress that can cause it to fail before it reaches material yield. Okay. All right, another one. So this is what I was trying to show you earlier, right? Just like it says in the question, take the top and the bottom as pinned. So K is just 1. It's steel, so we've got 200 GPa for elastic modulus and let's just say 250 MPa for the yield stress. Determine the maximum allowable force the column can support without buckling and apply a factor of safety of 2 against buckling, okay? The cross-sectional properties are this, so it's given in meters squared and annoyingly Ix is in meters to the power of 4. Okay, so that's in the x and the y direction, right? So we had to convert these, right, to millimeters. The way that I like to think about it is how do I cancel out the meters to the power of 4 such that I can get it in millimeters to the power of 4, okay? So we've got 1,000 millimeters per meter, right? And this, we put the entire bracket into the power of 4, okay? And the way this works is it cancels out the meters, right? Okay. So meters to the power of 4 gets cancelled out on the bottom of the fraction with meters to the power of 4. Now we're just left with millimeters to the power of 4, okay? So if I was to type this into my calculator, the way that I would do it is I would type this part times, times 1,000 to the power of 4, okay? And then it'll give you the perfect number that you need on your calculator. If you have this in scientific notation or whatever, which will be this, okay? You do the same thing with the IY value. So that was the IX value at the top. This is the IY value. Okay, what we're gonna do is because, right, in the XX direction, we've got the longer buckling arc, right, of 12 meters. And then in the YY direction, sorry, we have this S shape, right? So our length is only 6 meters. We have to check both, right? So we have to figure out which one's the more critical buckling, more critical value of force, which is going to reach buckling first, okay? So elastic modulus, we're going to plug in. IX, we're going to plug in. Okay, LX in millimeters is 12,000 in the XX direction. K, we're just going to take as 1. All right, so that gives us 1.197 times 10 to the 6 newtons, right? So that's buckling about the XX axis, right? So if I was to draw the beam, the column, that's how critical, that's the stress, that's the force, fuck, what am I trying to say? That's the force that would cause our column to buckle that way, okay? The force that's going to cause our column to buckle this way can be calculated with these terms now instead, okay? So what I've done is I've changed the IY value, and then also the L values can be halved as well, okay? So that gives us 1.031 times 10 to the 6, okay? So this one, since it's lower, right, it's going to happen first, okay? So it's a more critical direction. So in our particular case, this is why. The YY buckling happens first, okay? All right, and then last thing is we have to account for a factor of safety. So we get this number, and then we divide it by 2. So this is the allowable force. So we're going to take it as if only half the amount of force is allowed on it, right? Before it reaches buckling, okay? That gives us 515 kilonewtons, okay? One thing I want you to keep in mind as well is how much is 1 kilonewton, okay? Because sometimes, like, you don't really think about it. So if you imagine a tradie, okay, and this tradie weighs 100 kilos, if we do gravity force is equal to m times g, so that's his m, right? Weighs 100 kilos, and gravity, I know it's 9.81, right? But let's just take it as 10, because that's what we do as structural engineers, right? This gives us a force of 1,000 newtons, right? 1,000 newtons is 1 kilonewton, okay? So just remember it like this, okay? 1 kilonewton is 1 tradie, okay? That's roughly how much you can think of a kilonewton as, okay? And so 515 kilonewtons means this column can support 515 tradies, okay? before it starts to buckle, right? As an allowable force. Okay, the last thing I'm doing here is I'm checking if Euler's buckling formula can even apply. Okay, the reason for that is because if you have a curve that looks like this, right, a yield curve, Euler's buckling formula for early buckling only happens in the elastic region. Okay, so what we're doing is we're checking whether the critical buckling force, which was this one, divided by the area, which is this, which was 139.3 MPa, is less than 250 MPa, right? So since we're down here, we have a critical buckling stress of 139.3, which means buckling is actually going to govern, because buckling is less than the yield, or the compressive yield strength, right? Yeah, if that makes sense. Okay, so that's pretty much all. Do you guys have any questions about this in particular? Nope. Okay, thank you very much for coming to my classes.